Okay, we'll follow the same approach. The first thing we want to do is show the skeleton, the basic connectivity. So we have a CH3 here. And then we have a CH. Doesn't matter the angles that you show in this basic skeleton because we're not trying to show geometry yet, so you could just do up, down, straight across, doesn't matter. Then we have another CH, and then another CH, and an oxygen. Okay, so definitely missing a lot of octets. We're going to have to add in some lone pairs, some pi bonds to make every atom have its octet and have a stable configuration. And so remember, carbon likes to have 4 bonds, so I think one thing I can do is both of these carbons are missing a bond, so if I put a pi bond between these two to make a double bond, then that would satisfy both of those carbons. So this has 4 bonds, this now has 4 bonds, this has 4 bonds, and then what we could do on this end carbon is the same thing with the oxygen. We can form a double bond between the carbon and oxygen, so that carbon has 4 bonds. And what's the oxygen missing? Oxygen likes to have 2 bonds and 2 lone pairs. So we'll add on those lone pairs, and now it's got an octet as well. Okay, and that would have the right formal charge, 1, 2, 3, 4, 5, 6. Oxygen has 6, and it wants 6, so that would be a neutral oxygen. Okay, so really the low structures we should attempt to do by inspection rather than adding up all the valence electrons and putting them in and so on. With experience, we should be able to put these together fairly rapidly. Okay, how about the 3D sketch? Now again, atom by atom, we want to determine the hybridization because that's going to give us our geometry. So our first carbon has 1, 2, 3, 4 regions of electron density, so that is sp3 hybridized. Here we have 1, 2, 3 regions of electron density. That gives us sp2 hybridization. And notice if I kind of add up the exponents here, if I have 1 s and 2 p's, that is what gave me my 3 hybrid orbitals to accommodate the 3 regions of electron density. So hopefully this is something that ends up being somewhat intuitive. This carbon has 3 regions, so it's sp2. This carbon, sp2. And the oxygen has 2 lone pairs and a double bond. We'll count all those as separate regions, so it's also sp2. We have a lot of sp2 atoms here. Okay, so we can start anywhere we want. Let's start with our, just go left to right again. So our tetrahedral carbon for sp3 is tetrahedral. So we draw 2 bonds in the plane, a little wider than 90. And 1 bond is a wedge, and 1 bond as a dash. That's what every tetrahedral atom is going to look like. Okay, so what we have to put here are 3 hydrogens and a carbon. Now, what you should do is you should put the carbon in one of these positions in the plane, because what we want to do is put as many atoms in the plane as possible. If I put my carbon out here, out in front of the board, now the whole rest of the molecule is going to be floating out in front of the page, and that's going to be impossible to draw. So we want to locate as many atoms as possible in the plane, so let's keep the carbon chain in the plane. So then the other 3 positions are our hydrogens. Okay, now this carbon is sp2 hybridized. If you have 3 regions of electron density, you want to make it trigonal planar to get them as far apart from each other as possible. So we've already drawn 1 bond here, and now 120 degrees, we go down and up. It's about 120. Again, you know what 90 looks like, so we want a little wider than that. Really, 120 looks very much like 110. There's not going to be a big difference there. So we have a hydrogen and a carbon that we want to put in. We have a little more room to work down here. So let's put the hydrogen up here and the carbon down here. Okay. And this next carbon is also trigonal planar. So we'll draw a bond straight down and up that way. That's about 120 degrees, corners of a triangle. We'll put the hydrogen down here and the carbon up here. And then finally we have an oxygen and a hydrogen, another trigonal planar. Doesn't matter which way we put them, who's where, it's all good. Okay, now we want to show our pi bonds. We have a double bond between these 2 carbons and between the carbon and oxygen. And again, if we draw the trigonal planar in the plane like we've shown, then the p orbitals are orthogonal to that. They're perpendicular. They're going to be sticking straight out and straight back. So we could draw them as a wedge and dash on each carbon. There's one pi bond. And then on the carbon and oxygen, wedge and dash. So it's like we're tilting it just slightly so we can see both halves of the p orbital. And then how about these lone pairs? They're also trigonal planar, so they're in this region. We can kind of draw a line and show them. Last one example, we showed the orbital. Another option, sometimes you could just draw a line to show, not as a bond, but just showing the geometry that it's in the plane. Okay, and if we take a look at a model of this, okay, we have it flipped over here, trigonal planar. Trigonal planar, this part of the molecule is flat, and you can see the zigzag shape there, and this last carbon is tetrahedral, and we could rotate it any way we want. We had it the one where the hydrogen is up here. Okay, you could have also chosen to put this CH3 group up here. That would actually be a different molecule, so it's kind of bent this way. This we call a cis conformation. This would be a trans conformation about that double bond. Those would both be okay because this condensed formula doesn't tell us what shape the molecule is. We have a couple different options there. So those would both be acceptable.